Welcome to our NPTEL lectures on advanced power electronics and control. This will be a third lecture on single phase converters. We shall continue with the single phase fully controlled converter. It will be a half controlled device. It is this thyristors actually it will give a half wave control, because it will trigger in a positive half cycle and negative half cycle it will be reverse biased, and we are not supposed to use thyristors while it is reverse biased. So, gate triggering should be off. So, and let us assume that it is typically feeding a DC motor kind of load. For this reason, this is manifested by the RLE. R is the resistance of this motor, and thereafter there will be a huge field. It may be shunt or series motor, that is been represented by L, and the back EMF part will be actually pretty constant, because it will run at a constant speed, because electrical inertia is quite actually low compared to the mechanical inertia. For this reason actually back EMF will be proportional to the speed. For this we can assume that back EMF is almost constant, or you can think of it is a charging of a battery kind of thing also. So, the rate 1 indicates the load voltage. With the absence of the free wheel diode, you will get a negative portion. It is triggered at an angle alpha. Thereafter, it will continue till actually pi. Thereafter, we assume the discontinuous operation of the current, but due to this actually stored energy in the inductor, current will be actually flowing into the negative direction. Thereafter, once actually this energy is free, then actually it will be automatically commutated. Then it will be off, again the same cycle is repeated, but actual conduction angle is beta minus alpha, and where actually it is triggered at a delay angle alpha. Now, we require to see, there are a few parameters to analyze, that lambda is basically corresponds to Vm sin omega t. Vm sin lambda equal to basically the back EMF voltage. So, in this case what will happen? So, lambda equal to sin inverse back EMF by Vm. So, for the triggering angle there is a two conditions. When triggering angle is actually less than the lambda, then the thyristor conduct for basically lambda to beta, that conduction angle, and if alpha is actually more than that, because still it is not actually what happened basically, till the supply voltage is more than the back EMF, thyristor is not forward biased. So, for this reason even if it is triggered, so thyristor will not be conducting. Thyristor required to conduct after actually it has reached the voltage greater than the back EMF. So, for this reason same way the triggering angle alpha should be greater than lambda, and the thyristors conducts for an angle alpha to beta. So, Vs equal to Vm sin omega t is the input voltage, V0 equal to Vm sin omega t for the output voltage for alpha to beta, and V0 equal to back EMF for omega t equal to 0 to alpha for this condition, and for this negative half cycle, that is beta to 2 pi. So, we can actually find it out the conditions, and we can write that actually differential equations to find it out the load current, and its profile it has been shown in the waveform. When the thyristor is triggered at a delay angle of alpha, alpha is more than lambda, then equations of the circuits can be given as Vm sin omega t equal to IR plus L di dt plus the back EMF for this duration. Now, in general expressions for the output, so we can write that actually you can solve this differential equation, and you can find it out that the load current will have Vm by Z sin omega t minus phi. We have discussed phi in previous class, where actually phi is basically this one, tan phi equal to actually omega L by R. So, by E by R plus this term A e to the power minus T by tau, but tau is the electrical time constant of the system. So, this is the Z value, Z is given by this thing and tan phi is actually omega L by R. Similarly, the tau time constant is L by R, the load circuit constant, and general expressions for these things, if we substitute, then we will have actually this value. Then what you can do, we require to find it out the value of A, that is unknown. So, we require to find A, which we have done in case of the diode based rectifier also. So, by initial conditions. So, when current is 0, for this reason A actually apply the initial condition when omega t equal to alpha, then load current I 0 equal to 0. So, if we can equate it, I 0 equal to 0, that equal to Vm by Z sin alpha minus phi minus E by R plus A e to the power minus R by L alpha by omega. From there we can get an expressions of A, and that will have a component of e to the power. So, it is a varying component, you can see that it is a constant, thereafter a sinusoidal component, and it is varied via actually an exponential component. So, here minus sign is missing. So, substituting this value A, and we can have an expressions actually the load current. So, load current will take this format. So, Vm by Z sin omega t minus phi E by R plus E by R minus Vm by Z sin alpha minus phi e to the power minus R by omega L omega t minus alpha. So, from this equation, this term, this sinusoidal component can be 0 if you trigger alpha equal to phi. So, ultimately then this sinusoidal component will come out, you will have a sinusoidal component plus a decaying component, this will be a decaying component. Now, let us take a next class, that is a basically full control converter with a central trap topology. So, midpoint is available because you have because in that configuration negative cycle is totally omitted. So, for this in conversion ratio is very poor, and you also have a high degree of actually ripples. So, for this reason we prefer actually full control mode of operations. So, but problem is there, if you use a transformer, we require the central tap transformer. So, same condition arises. So, let us consider that for RL load first. So, we have a continuous and a discontinuous operation of the load current. Once we have a, this is the current, you can see there is a discontinuous mode of conduction. The red line shows that this is basically the voltage output available across this load, and this is the free wheel, it is optional whether it is connected or not, it generally comes with a switch maybe. So, this waveform, this fast waveform shows that discontinuous load current for the central tap full control converter for triggering angle alpha for without any free wheel diode. So, diode is basically not been placed into the circuit. So, for this what will happen? So, negative voltage will come, that gives rise to the ripples or more DC, and thereafter it will trigger an angle alpha, then it will conduct. So, stored energy will make these thyristors to conduct even in the negative half cycle. So, you get this profile. So, all the energy is discharged during this time. So, for this reason there will be no voltages across available, and same way it will continue. If we have discontinuous conduction with the free wheel diode, then this negative part get truncated, there is no negative part. So, what happen actually till load voltage will be positive and DC component will be more. So, what happen then thereafter actually at this point actually thyristors will be reverse biased due to the diode, and free wheel diode come into the picture, and current will free wheel through this path. This is the free wheel direction till actually energy stored into the inductor is dissipated, that is for the duration pi to beta. And if the load current is quite high, then you may have a continuous conduction mode, and in this case you can see that actually current still follows alpha. Thereafter what happened, since thyristors is conducting, you will be actually, this is without free wheel. So, for this you get a huge part of the negative voltage. Then actually thyristor will be triggered at an angle alpha. So, forward voltage you will get across the load. Then what happens is thyristor is actually in a forward conduction mode due to the high current, ultimately it will deliver negative load voltage. So, similarly it will continue. So, negative load voltage can be truncated with the use of the freewheeling diode. Now, let us see there is a characteristics of this actually single phase fully controlled converter. So, we will plot VDC versus alpha. So, you can see that you can get a maximum value of VDC, that is 2 Vm by pi, and that is at alpha equal to 0. So, control characteristics of the single phase, and we assume that actually load current is continuous for this reason and without the freewheel diode, that means this waveform. So, then what will happen, you will find that at 90 degree. So, this voltage delivered to the load is 0. Thereafter, if you increase this alpha beyond 90 degree, then you will a conversion operation. So, it will be a bipolar. So, you can convert AC to DC as well as you can reconvert it into the DC to AC. So, actually, so that load itself will actually then supply back the power to the source. This kind of application is possible in case of the regeneration. So, at 90 it is 0, if it is actually 120 degree, then you can see that it is minus VDM, so on, as 180 degree. So, it is the totally the inversion or inverted operation. So, let us consider that RLE load with bridge configuration, where actually we can bypass this central trap transformer, and also actually we may not require transformer if it is directly fed from the source. So, now in forward half cycle we shall put this thyristor in such a way that thyristor T1 T2 will conduct, and we assume that actually load current is actually continuous and constant. That means it has got a very high value of inductance. Generally this can be approximated when omega L by R ratio is around 10. So, time constant is around 10 seconds. So, for the period of actually 20 millisecond, it can be assumed to be actually constant. So, it has been triggered at an angle alpha. So, before that the pair of thyristors in negative half cycle was conducting and you are getting a negative voltage, and thereafter and same thing is applicable. So, since load current is continuous, so back effect of the back EMF may not be seen. So, thereafter thyristors is triggered at an angle alpha, it will conduct till alpha to pi plus alpha. So, 180 degree, thereafter again T3 and T4 will come into the picture. So, it is quite easy to analysis, since load current we have assumed this kind of fashion. So, the source current will also have a square wave, and we can do the Fourier series analysis. All the odd harmonic will be present for the odd wave symmetry, and thus we can calculate what is the amount of the actually VDC and RMS and the corresponding current part of it. So, VDC actually 2 Vm by pi cos alpha. So, we can derive that expression by simply by integration. Same way actually the RMS output voltage will be Vm by root 2 will be Vs, and current to the thyristors will be actually square wave. So, this will be the current through across T1 and T2 for the period of actually 360 degree. Similarly, this will be the current for T3 and T4. Now, here this is a 2 quadrant operation. So, while discussing switch, we have described the quadrant operation. Here current is unidirectional. So, current is always positive in the load, but voltage can be negative and positive depending on the triggering angle. So, if alpha is actually more than 90 degree in this case, then it will be an inversion operation, and if alpha is less than 90 degree, you get a controlled rectifier operation. Now, let us see the condition when there are 3 changes has been made. This is called half control. You can have a different combination of half control. You can as asymmetrical or symmetrical configuration. So, here upper 2 are thyristors, lower 2 are diode. We can have another configuration where one leg is of thyristors, another leg is of diode. Then if you do that, then we did not have to give actually the freewheeling diode in that case. Let us consider this configuration. This configuration is called single phase fully controlled rectifier. This is a single phase semi controlled converter rather. So, and it is feeding a RLE load. So, it is omega t equal to alpha, it has been triggered, and we assume that load current is quite high and continuous. So, actually it will fit till omega t equal to 2 pi plus alpha. Thyristors T2 is triggered at an angle pi plus alpha at 3 pi plus alpha. So, accordingly this time delay between T1 and T2 is going to be the 180 degree. So, see that what kind of waveform voltage you will get it. So, you have triggered here, this is your angle. So, ultimately you will get a voltage like this, and please see that since the diode into the pictures. So, negative voltage it is not possible to have, because diode will conduct and free will truncate, this is actually the negative voltage, and thus this part is been actually omitted. So, you only get the first quadrant operation, that is the actually the rectifications or the converter operation. Same way current through this thyristors is T1 and it is T2, and this is a D1 and D2 so on, and this is a single quadrant operation. Now, actually this is IA, this is a source current, and it will conducting for a very small interval of time alpha to pi, that are pi plus alpha to 2 pi in negative half core, but since the value of the inductance is so high that you get a constant actually the load current. And similarly, you can find that rest of the current is flowing through the free wheel diode. Current through the free wheel diode will be very high, and this is the amount of the current flowing through the free wheel diode. So, thus T1 and D1 conducts for this duration for alpha to pi, T2 D2 conducts for the period pi plus alpha to 2 pi, and for omega t 0 to alpha, that free wheel diode conducts again pi to pi plus alpha free wheel diode conducts. So, this is the waveform of it. The pink line actually shows the load voltages, and from there we can derive the equation of the load voltage, that is actually VDC, that Vn by, if you integrate over it, it is a very simple thing, you will get Vm by pi 1 plus cos alpha. So, you can put any value of the cos alpha, you can find that actually even if you put cos alpha equal to 180 degree, this value will be 0. So, we will have a single quadrant operation. Same way we can actually find it out the RMS value by actually integrating over it. So, we can get Vm by root 2 1 by pi minus alpha plus sine 2 alpha by 2. So, you can expect that in voltage there will be some oscillation of the double frequency. So, due to that double frequency oscillation will come. So, if you divide by R, definitely you get the IRMS, and if you divide it by R you get the IDC, which is assumed to be constant in this square wave kind of thing. So, and mind it, since it is a square wave, so average and RMS value should be same. Okay. Now, let us come to the single phase dual converter. So, it is a 4 quadrant operation. So, this thyristors is a full control converter. So, thus it can operate plus minus actually 0 to 90 degree as a mode of converter and 90 to 180 degree as a mode of the inverter. Same way, but you see that polarity of this actually thyristors is reversed. So, for this reason it will be minus alpha, and since that there can be this pole voltage may have a instantaneous difference of the voltages. So, due to that you require to actually put a current blocking inductor, so that it can block the instantaneous voltages between these two pole voltages. So, what happened in first mode, let us assume that this is the input voltage and essentially you have chopped out this voltage, and since it is a full control operation you get this kind of waveform. And similarly you feed the same voltage, and if you trigger, the logic of triggering of this dual converter is that if you trigger that one converter at an alpha, another converter required to trigger at pi minus alpha. So, you have triggered pi minus alpha. So, essentially you will get actually this part of the voltages. So, essentially what you will get at the output voltage is V1 plus V2. So, this will be the voltages across the load, and unfortunately due to that there will be a circulating current flowing like this when there is no cancellation of the instantaneous voltages. To block that instantaneous voltages we have put an inductor. So, let us do some analysis. So, of course, since it is a full control converter, for first converter in left hand side it is this value will be this average voltage, or the VDC1 will be 2 Vm by pi 1 by cos alpha 1. Similarly, output voltage of the second converter VDC2, that will be 2 Vm by pi cos alpha 2. The dual converter operates one in a converter operated as a control rectifier, another actually which triggering angle is less than 90 degree, another is basically it has to be more than 90 degree for the, and we hold this equation for this. If it is triggered at alpha, another is triggered 180 degree minus alpha. So, VDC1 should be equal to minus VDC by 2. So, if you can equate these two equations, ultimately you find that basically alpha 2 equal to pi minus alpha 1. So, this is the constraint. So, alpha 1 plus alpha 2 should be equal to pi. So, for this reason this mode of operation is been continued. So, dual converter can be operated in two different mode of operations definitely. So, one is non-circulating current, circulating current free mode of operation. We can make the instantaneous voltage same at all the time, so that no circulating current flows, and circulating current mode of operation. So, in non-circulating current mode of operation, this mode only actually possible in one instant. Mode is in this mode only one converter is operated one time. So, both converter are not operated. So, when converter 1 is on, that means alpha 1 should be equal to 0 to 90 degree, and VDC is positive and IDC is also positive, and where converter 2 is on, it should be actually less than 90 degree, and VDC is negative and this should be also negative. So, then what happens, since you are operating one converter at one time and thus there is no condition of flow of current. But what happens then, actually power delivering capability is decreasing. In circulating mode, what happens, in this mode both the converter are switched on and operated at the same time, and the triggering angle alpha 1 and alpha 2 are adjusted in such a way alpha 1 plus alpha 2 equal to 180 degree or alpha 2 equal to 180 degree minus alpha 1. So, when this mode is generally more preferred. So, when alpha 1 is basically less than 90 degree, converter 1 operates in a control rectifier and converter 2 operates in a inverter mode, and in this case VDC and IDC are both positive with the preassumed directions. When it is changed, when actually this condition is satisfied, that is alpha 1 is more than 90 degree and less than 180 degree, then converter 1 operates in the inverter mode and converter 2 operates in a rectifier mode, and thus what happen, we get a negative DC. For this reason we have a 4 quadrant operation. So, converter 1 is in rectify mode, thereafter converter 1 is inverting mode, this is one of this quadrant operation. In this condition IDC is positive. So, this is a conversion, this is actually we have described in case of the full control converter. Similarly, we can make converter 2 less than 90 degree, then what happen, basically IDC will be negative, but VDC will be positive, and this is a third quadrant operation, both VDC and IDC both will be negative, where actually you are putting the converter to more than 90 degree. So, let us understand and the few aspect of it. So, let us assume that the instantaneous output voltage of converter 1 is V01 and instantaneous output voltage of converter 2 is V02, and the circulating current R we require to calculate and we require to block that circulating current, which may harm actually the thyristors unnecessarily, because it is not getting into the load. Circulating current IR can be determined by integrating the instantaneous voltage difference, which is the drop across the circulating current along LR. So, let us start at omega t equal to 2 pi minus alpha 1, as the 2 average output voltage during this interval is omega t equal to pi plus alpha and another is 2 pi minus alpha, positive and opposite to their contributions. So, we can put these limits. So, IR equal to this thing 2 pi minus alpha to omega t, where actually VR is this. So, we can actually find it out the what should be the value of this circulating current. Substituting V01 equal to minus Vm sin omega t for 2 pi minus alpha 1. So, you just substitute it and you get the results IR equal to 2 Vm by omega Lr cos omega t minus cos alpha. So, you can see one thing, that you can actually make the circulating current 0 suitably controlling the alpha 1, but it is not possible most of the time. So, for triggering angle alpha equal to 0, the magnitude of the circulating current becomes minimum when omega t equal to n pi. So, magnitude become maximum, and when omega t equal to n pi actually for the odd harmonics, the peaks of the load current IP, one of the converter is actually giving you the current. So, this is with the expressions of it. So, IP plus 4 Bm by omega L. So, where IP equal to IL max, that is equal to Vm by RL, and that is IR should be equal to, this is a max peak value of the circulating current, that is 4 Vm by omega Lr. I continue with the next class with this converter. We are looking forward to discuss more interesting detail about this converter. Thank you.